friends to form a team, okay, of 3, okay, because you have we have how many supposedly? How many students? 69 supposedly. Yeah, but today, because of the requirement from the department, we need to fill out some questionnaire. So we use some reward, okay, to attract more students. Otherwise, I mean, yeah. So how many students showed up today? 20? Yeah, still much lower than what we really have in this class, okay. But anyway, okay, because we have close to 70 students, so if we give maybe 10-12 minutes per group to do the presentation, you know, I don't think we can do 2 students per group. That's going to be too many teams, okay. So we will do 3 students for each group, okay. So if you have not found your teammates, okay, it's a good time to look for it, okay. Yeah, I would like you guys to submit your team information along with your homework 3. Of course, I haven't posted the homework 3 yet, okay. So I will post the homework 3 maybe a week from today, which has the deadline the second following week, okay. So hopefully you will have more than 2 weeks of time to look for your teammate, okay. Of course, as I said, I will also post the final project this week, okay. So this is the first thing, okay. Well, and the second, I mean, which is about homework 3, okay. And the third one, okay, is because I have a paper accepted by a conference, so I will be out of country. Let me see. I'll be out of country in the week of the what's that? Yeah, it's the week of May 17th to 19th. Okay, I believe 17th is a Wednesday, which happens to be our class. But I will have to be in US on the 17th. So I most likely will fly to US on the 16th. Okay, so pretty much that week of lecture, I will have to cancel that week of that lecture, okay? Of course, I will not, okay, because 17 to 19, that week is actually very close to the finals, right? So, and this is really an unexpected event, okay? It's not you know, like last week it was a holiday, okay? It's not, you know, everybody get a day off, you know? But this one is just for my my academic you know, research reason. So I will have to move all the events 1 week later. Okay, you know, we have 2 weeks what do they call it? A buffer or something, you know, for teacher who would like to extend the lecture, you know, because originally the lecture should be over at the end of May, okay, but I think I set up the presentation to be on the first week of June, right? the presentation will be first week of June. But now, okay, because of this, to compensate the lecture, okay, that I will be missing like on the May 17th. So I will, you know, for the first week of, I will move like the final exam to the first week of June, okay, and the presentation to the second week of June, if I remember correctly. Okay, please check your syllabus to confirm that. Basically, it's like a 1 week, you know, I'll give you back that 1 week of lecture, okay? So this is the, also important. So please do not come to the lecture on the May 17th and tell me like, well, how come there's nobody here, okay? Because I already tell you guys, okay? I will also have the have the TA to announce that, okay, in the course E class website, okay? Just in case if somebody didn't come to the class today, okay? So, okay, come back to what we haven't finished the last time, okay? Last week, not last week, actually, last week was a holiday. The week before last week, okay? We talked about the linear regression, right? And, yeah, and, wait a moment. Yeah, we create a bunch of points, and we try to, create a linear regression model, okay, to fit a line, okay, to these points. And but when we check, okay, the result of the alpha and the beta, where alpha is the intercept, and the beta is the slope, okay, of your linear function, okay, and we find that they are highly correlated, okay. This is actually not a surprise. Remember, we talked about this. This is not a surprise because like they will all have to go through the mean of your points, okay, which is mean x and the mean y, okay, these points. Where is those? Where are those? All these points, all these lines will have to go through the mean of x and the mean of y. And because they have to go through this fixed point, and you can imagine, okay, yeah, we have this wheel of fortune phenomenon, because like because all this, all the alpha and the beta pair assignments have to, make sure this line will go past that particular point. Say, well, I think there's a yes. Assuming this is it's terrible. So think about this. Assuming this is the point, okay, where you get the x mean and the y mean. This is the point. So what happens is that, okay, because all the line has to go through this point, so you can see that, okay, for example, if you have like a larger slope, such as like here, okay, this is a positive slope, so you can see your intercept is lower, okay, if you have a larger slope. If you have a lower slope, okay, this slope is below 0, okay, it's a negative, okay, and you can see your intercept is actually higher, right? Of course, this is just an example. It depending on where this mean x and mean y is located, okay. You may end up having different relationship between the alpha and the beta, the intercept and the slope. But you can see that, okay, they have this relationship because they have to go through this middle point. Of course, obviously, okay, if all the points are ranging along this a particular line, such as what we have here, you can imagine, okay, the chance for the line to go on this direction is higher. For example, yeah, the chance for the line to go this direction is higher. But still, okay, as we know, like we are going to generate the posterior, okay, for your alpha and the beta, right? So when the alpha and beta change, because they have this relationship, so if you have a lower slope, okay, you may end up with like a higher intercept, something like that. So which eventually create such and you can see it is like concentrated at the middle, which actually represent like the lines that still going through this direction, but it can wiggle a little bit, and when it wiggles, you can see that, okay, well, you can see that the alpha and the beta has this very special, relation, and this correlation, okay, very close correlation between variables in the model is a bad thing for sampling, okay, for sampling technique, okay. That's actually the reason, okay, if you look at this one, okay, you may feel like strange that, okay, here, okay, we are sampling 2,000 points, and we use 1,000 points to tune before we get the next 2,000 points. Well, obviously, I mean, if you remember the example we had previously, we normally just collect 1,000 samples. And also, I mean, before collecting that 1,000 sample, we normally just use 500 points, 500 samples, I mean, to tune the parameters, okay, when we do this sampling. But the reason to increase number of sample and to increase the number of the sample to tune the model, okay, is because of this high correlation between your variables, okay. It will make the sampling algorithm less effective. I'm not saying it's you cannot get around with that. We still could, I mean, but it's just like it's going to take more effort. Okay, that's why, I mean, we use more points to tune the parameters, and we try to collect more sample points. Okay, this will become more clear when we get to talk about a sampling technique. Okay, hopefully after we finish this this chapter, I think we should be able to finish this chapter maybe in another 2 weeks, and then before we go on to talk about the GLM, generalized linear model, I would like to talk about the sampling technique. Okay, the MCMC, because I mean, every time you see a code like this, okay, just this is a magic, right? You just call this function and it will do the trick for you, but you really don't know what's inside of this function. Okay, yeah, I mean, I think I should tell you, like, not like the textbook actually try to talk about this like at the end of the book, okay, chapter 8, but I don't think that's a good way. Okay, personally, I don't, because the textbook wants you guys to learn how to do Bayesian data analysis. As for like the mathematical concept behind this Bayesian data analysis, they will just just try to hide those detail, okay, from you, and assume that, I mean, well, if you can write a code to do that, that's good enough. But personally, I think we are not like a mathematics department, yeah. So we don't talk about like proof that much, but still, I would like you guys to understand a little bit about the concept of how this sampling is done. Okay. Otherwise, there are some considerations. For example, like this type of tiny details. Why, when your variables are highly correlated, it's bad for the sampling. I mean, if you don't know the sampling technique, you wouldn't know about this. Okay, so of course, so when you have such a problem, okay, this problem obviously, I mean, is common in, for example, like linear regression, right? Because in the linear regression, when you are given a number of points, I mean, most likely your lines, okay, the regression line will go over the average of x and y. So if that's the case, how do we do? How do we get around? Okay, I mean, the first way, as we have seen, like we can increase the sampling points, but still, this will make your sampling ineffective. So, is there like other way we can get around with this? Yes. Okay. Actually, it's much more easier than you may think. Okay, we can modify the data before we run the linear regression. Okay, we can do like we can change like x to be x prime. Okay, where x prime is x minus the average of x. Okay, think about this. If you replace x with x prime, what is going to happen? Because you are going to work on the x prime, the y prime. where x prime is x minus x bar, and maybe it's yeah. This is like you know, the original function, and now we are regressing on this formula. Okay, the alpha prime and the beta prime, okay, will be, you know, obtained by using the x prime and the y. Okay, and you can see that, I mean, you can replace x prime by x minus x bar, right? And then, you know, put this back, okay, to be like this, where you can see this x bar is the average of all the average of the x coordinates of all the points, data points. Okay, so this is a fixed value, right? So alpha prime minus beta prime times x bar is a value. Okay, this is a value, and you can compare this one with this one, and from here you can identify that this well, with the original one. Well, original is y. Original is y equal to alpha plus beta x, right? This is the original linear regression function, right? So this is like after you replace x by x prime, what you are going to get. Okay, so you can see just by a very simple comparison, you can tell your beta is going to be the same as beta prime. The alpha obviously will be different, right? The alpha will be different. Okay, but this actually, okay, will move your that point, okay, that, I mean, original we circle on at that point. Now it will move that point, okay, to the center. Okay, it will move the point to here. Okay, originally assuming it's somewhere here, but it will move the point to here, and so when because the intercept is going to be, okay, this intercept alpha prime minus beta prime times x bar, okay, this beta prime times x bar, okay, this alpha prime is this is going to cancel out. Let me see. No, this is equal to the original alpha, and if I remember correctly, I mean, we can get the beta equal to beta prime, and also not this one. Okay, yeah, here. Okay, we can get, I mean, the x. Once we get this this estimate, we can get the original estimate back. Okay, because this is a simple variable replacement. Okay, so this is a trick you can do, okay, to remove that correlation between these the intercept and the slope. Okay, if I remember correctly, this actually get rid of the slope. So your wheel of fortune, okay, will still control the slope. The slope will still be, you can still, derive slope from here, but the intercept is gone. Okay, so the variable correlations will no longer be there. Okay, this is like the reason we can, replace the x by, x. I mean, we can use the x minus x prime, okay, to replace x, okay. So in addition to this trick, okay, we sometimes also would like to standardize the data, okay. So not only we get rid of the average, okay, we also try to divide for each point. We not only get rid of the average, okay, the average x, average y, we also divide the standard deviation of x, standard deviation of y, okay. By doing so, okay, we make sure like all the data, okay, all the dimension have the same scale, okay, have the same scale, okay. This will make our model, I mean, easier, okay. For actually, there are several reasons for that. First, okay, the first advantage, okay, after you standardize the data, okay, we can always use the same weekly informative priors without having to think about the scale of the data. As I said, like, because the scale pretty much for each dimension will be the same, okay. So the intercept will always be around 0, and the slope will be restricted to the interval -1 to +1. So this is a very good property, okay. Yeah, I remember correctly. The intercept will always be close to 0. So that breaks like the relationship between the intercept and the slope, okay. And another advantage is that, okay, I'm not sure if you guys are familiar with the z-score. Okay, the z-score basically talk about the data, okay, by something like, okay, oh, this value is like, it's -1.3 in this z-score unit. Okay, what does that mean? It means like it is like 1.3 times standard deviation below the average. Okay, so the z-score just indicate like how far away in terms of standard deviation, okay, the value is from the average point, okay. And to talk about the data, okay, by the z-score is a very convenient and a very meaningful way, okay, for communications. Okay, if you tell somebody, okay, well, this is for example, if you see, oh, this is outlier, you just say, oh, this z-score is very high or very low, okay, and everyone who deal with like data, okay, immediately get your idea. Okay, you don't have to say, oh, this data, okay, it's average something, and it's a standard deviation something. Oh, because of this standard deviation is this, and the mean is like this, and this data point is that value. So okay, we consider this as a outlier. No, we can just simply say one value. It's z-score. Okay, and the z-score convey a lot of information in there. Okay, and also because z-score allow us to talk about different dimensions at the same scale. Okay, it is much easier. Okay, for when you explain the result of the data. Okay, analysis. Okay. So here, okay, we can explore the posterior using AVIS, okay, and by using the plot trace, okay, and the summary, okay, and so you can see that here, okay, we are able to generate, okay, this is like we use the average intercept and average slope. And remember, this one is after we use like the variable, the x prime equal to x minus x bar, right? So we have to convert it back. Okay, otherwise, you know, it's going to be y equal to, you know, something close to 0 plus maybe close to 0.94 and x bar, x, okay, I mean x prime, I'm sorry, x prime, where x prime equal to, you know, x minus x bar. Okay, so you have to get that thing back, okay, and it'll look like this. But so the average intercept looks like this, and average slope, okay, looks like that, and the line, okay, is indicated by this dark straight line, and the gray color lines are what you get, okay, from the posterior predictive check. Okay, you sample some values and try to reconstruct that line, okay, from the posterior of alpha and beta, okay, which is like indicated here. But we have some more way to visualize the result, okay. For example, okay, here we can use there's a function called like az.plot HPD. This function allowed us to, you know, draw the result something like this. It's going to look like, okay, this is the bound, okay, of your variance, and everything in between, it will fill the void for you. So it looks nice, okay. So this is like another way you can verify, okay. You know, as I say, like this is like you know, just posterior predictive check number 2, okay. Either the first one or this second one, okay, are okay. We even have the third one. The third one is like you know, tell you how you can, you know, utilize this az.plot HPD. I mean, you can even set like a credible interval point equal to 0.5, and the other one just use the default one. The default one is the 94 you know, HPD, okay. This one is 0.5 means like 50% HPD. So you can imagine 50% HPD is narrower, right? And 94% HPD is wider. So the result looks like this. So this is the range you get by using 50% HPD, okay. And the outer, you know, the outer shape, I mean, indicate like the 94 HPD lines you could possibly get from this posterior, okay, and which obviously cover this data point very well, okay. So this function, okay, is a helper function, and we can use to plot HPD interval for linear regression, okay. By default, the function smooths the interval, okay, just like what I told you, okay. You will fill those like the area in gray, okay. But you could pass the argument, okay, smooth equal to false, okay, and it will look very different, okay. I mean, I will leave that to you guys. You can check it out, okay. And so here's the thing, okay? So we have like some data point, okay, with the x and y value pair, right? And one way we do it is like we try to consider x as like the input, and we predict y, right? Okay, like what we did, I mean, previously. But we can also consider x-y pair as, you know, we can consider x and y as like what should I say, like different attributes, different features, okay? And we could consider, okay, so we want to measure, for example, the degree of dependence between two variables, okay? In this case, it's x and y, okay? So the common measure, okay, how do you measure the dependence between two variables, okay? You know, it's like the Pearson Correlation coefficient, okay? So we normally indicate it as a r, lowercase r, okay? So when r is, you know, 1, okay, plus 1, we have a perfect positive linear correlation. When r is negative 1, we have a perfect negative linear correlation. When r is 0, we have no linear correlation, okay? So you may feel like, well, when we talk about this Pearson correlation coefficient, I mean, when I talk about this coefficient like that, it looks to you that it's a slope. In some sense, it does have some relationship to the slope. We'll get to that point later, but it is really not the slope, okay, in general situation, okay. I mean, here we show you some image, okay, from Wikipedia, okay. From there you can see that, okay, why I say like, you know, the R value or the Pearson correlation coefficient, it doesn't indicate the slope. For example, here, both of these are 1. Because obviously both of them represent a very good, you know, linear relationship. But they may have different slope. Okay, they may have different slope. Okay, and as the points gets more you know, diverse, okay, you can see the value reduced from 1 to 0.8 to 0.4, and when those points are really like have no any particular relationship, okay, we say it's a 0, and you can see, I mean, no matter what the slope it is, okay, it is always 1 until okay, when you have a, you know, horizontal line, then the correlation is 0. Okay, obviously because we are looking for their relationship, right? So I mean, the Pearson coefficient is like, okay, when one value increase, whether or not the other value also increase. But if it's like horizontal, you know, really you cannot show any of that relation, even though it is a linear. I mean, it is a linear relation, but you know, the Pearson correlation is 0. Okay, and as long as you have a negative slope, no matter how you know, how low, how you know, how much lower, okay, your slope is, okay, it's always -1. Okay, and you could have like some very interesting like point distribution, and all this, you know, you get the Pearson correlation 0. So remember I told you the Pearson correlation has, you know, could have something to do with the slope. Okay, so here's the thing. Okay, so you could represent the Pearson correlation as like a beta times sigma x divided by sigma y. Okay, this sigma x is the standard deviation of x. Okay, divided by standard deviation of y. Obviously, okay, when these two variable, okay, these two variable have the same scale, okay, or when these two variables, okay, are standardized, then the Pearson correlation coefficient is going to be, you know, just slope. Okay, just like slope. Okay, so you know, so this is another reason, okay, that standardizing the data set, okay, the advantage standardizing the data set brings, okay. So but keep in mind, Pearson correlation coefficient, okay, has a different way, has many ways to compute it. Okay, this is not normally like the way to compute the Pearson correlation coefficient. In general, the way to compute the Pearson correlation coefficient is from what we call determination coefficient. Okay, which is normally indicated as a R square. Okay, from the name you can immediately tell. Okay, it's a square of the Pearson correlation coefficient. Okay, normally it is like that. Okay, so and this R square. Okay, sometimes we write it R lowercase r square or uppercase R square. Basically, we are talking about the same thing. Okay, it is like you know, defined like this. So what is this? Okay, so this is like the portion of the variance in a dependent variable. Okay, dependent variable is y. Okay, so this is like the expected here. Okay, it's an expected value y hat over s posterior samples. Okay, that lowercase the superscript s means you get s posterior samples, and you can estimate that the expected